1 minute and you can start. It's visible for me. It's visible, I think, for all us. Same. Yes.
Okay, so thank you very much for giving me the opportunity to present in this conference. Of course, I support Ukraine, and I hope that you guys will overcome Mordor sooner rather than later. So, what I want to talk about today is a subject that fascinated me for a long time, but unfortunately, it's somewhat tough to do stuff in that, which is a braid group action on homology and moduli dimension of moduli spaces. Uh, so let's first look on the problem statement. I'm looking on elliptic curves. So I'm looking on complex curves of genus 1. And the question is what kind of functions we can produce on it. So when we talk about functions, we always look on divisors. But other than divisors, you have other stuff like, for example, branch points and whatnot. So you can give parameterization not through divisors like the poles and the zeros, which are actually determine the function completely. But you want to ask, okay, what about how can we actually approach and discuss whether existence of functions with other conditions? So what I want to do now, I want to formulate a simple computational criteria to answer this type of questions. Okay, what functions are actually available using braid group and homology action? And unfortunately, this is just a criteria that I'm aware in genus 1. Probably it can be generalized, but I'm not sure how. So let's look on, on an example of such a problem. So consider an equation in two variables, fxy equals 0. So it's well known that it has that every root has the n roots counting multiplicity. And there is a finite number of points in lambda where we have less points on the fiber, and we call those points ramification points. Okay? And for each ramification point, you have a preimage. And if you count the preimages, right, it will be always n. So, but you can have less preimages for each ramification point. So this is an example. Consider, for example, something of the form y cubed equals x minus lambda I, and then the ramification points are lambda i's. Now, in those ramification points, the coordinate is not going to be 1 to 1, it's going to be 3 to 1, and you can see it by, well, because I'm going to define the coordinate on the point as x minus lambda I cube, or a coordinate will be t cubed plus lambda I. So this kind of represents the fact that 3 points are coming together on a curve. Okay? So how this ramification behavior works is a little tricky. So it is encoded by behavioral function by if you take a base point, which has exactly n preimages, and then you surround the loop around this branch point and analytically continue across it. So if you selected one preimage on this branch point, right, it can go to another preimage, and then we are going to talk about permutations. Just like we had, so it's basically a permutation representation, as Ruslan was telling us. But of course, Ruslan is much higher sophistication than this simple thing. Okay, so for each loop, if you look on the complex plane, for each loop you have this kind of a presentation. Okay, and it induces a permutation representation for each sigma I. So these are the schematic loops that is given below. And you can see that if you have a branch point, the loops are actually rotated around the branch point. Why are they rotated around the branch point? Because when I'm describing the action of this cover, right, of this function, I actually want to throw the branch points away. Okay? So I'm on a sphere. Okay? That's why I'm throwing also the infinity out of the way. And you know, you can think about infinity as being one of these branch points. Okay? So now it turns out that the converse is also true. And if you have this kind of a permutation representation, okay, you can create an algebraic curve that will actually give this permutation representation. This is actually summarized in Riemann's existence theorem. This basically the main result on algebraic curves that Riemann have proved above the complex numbers. Above other fields, it's more complicated. So you have a H1 to HR permutation representation in the symmetric group, which satisfies the following two properties. The product is 1, and HI acts transitively on set 1 to n. Then there exists a compact algebraic curve X and a mapping from X to CP1 such that the permutation representation associated with X is precisely HI. Okay, now why is the first condition? The first condition is coming from the fact that this is a sphere. And if you look on these loops on a sphere, you will discover very quickly that their product must be 1 because you have the homotopy to take it out from the other side. If you picture the sphere, you have points, you can actually take this loop, the product, and kind of take it into the trivial loop from the other side, which it kind of doesn't cross these points. Because we are talking about, you know, covering from the algebraic curve to the sphere, we have this, first condition. The second condition just says that you have a connected topological space upstairs. Otherwise, if it's not transitive, you have kind of two pieces. So we want to avoid that. Okay, and this theorem is actually proven very straightforwardly. I mean, in any topological course, when you talk about complex analytic continuation and topological spaces, you take the cover of the space without those points, and then you put those put the points back in based on this permutation representation. And this is kind of a schematic way to think about it. So here you have the presentation, you have a 4-to-1 cover, and you have a permutation representation of 1, 2, 3, 4, and you can see that you kind of here on those two guys, you have no problem to fill in the points. Here you have to actually fill with a disk here with z go to z square, because those two guys have a cross or have a bridge. I call it as a bridge, and here I'm utilizing my very bad picture
Singular point.
qualities to actually kind of try and visualize it. And visualizing that is not very easy, even for me. I mean, it's always mystery how Riemann actually did it in almost 200 years ago. I mean, it's crazy.
Is it
Now-
singular point was?
Well, it's not a singular point, right? A singular point you cannot compactify. Here on algebraic curves you can. So it's not a singular point, right?
Yes.
But look, remember that Riemann actually did this when he was 19 years old. So it's kind of shocking that a 19-year-old guy could come up with this kind of pictures. Okay, now suppose we have this kind of construction, right? What I want to ask, right, is how many curves carries this kind of function. So we produce one curve, but we want to find more curves like that, or to say something about the set of these curves. Okay. So what can we say about the set of algebraic curves that carry such functions? So this theorem, right, will tell us that we have one curve, but it doesn't tell us any additional information about them. For example, if I have this kind of a permutation, does every curve of genus G carry such a function? So I'm going to answer this question for a G equals 1 curve and show an example of how to use it. So, so I want to emphasize that the criteria that I'm going to formulate is not a criteria which is abstract nonsense that is impossible to calculate. It's actually a very down-to-earth criteria that can answer questions and prove theorems. Okay? So we want to formalize the problem. So in order to formalize the problem, we need to start moving these points around. So here, the points are static. What I want to do now, I want to take these points and start to moving them around. When I move them around, I actually move points which are different from each other on the sphere. Okay? And the configuration space, when these points are moving around, is going to be CPR, the projective space minus the discriminant locus. The discriminant locus is just basically a fancy way to say that we don't want the points to come together. So we throw all the points where at least two coordinates are equal in CPR. Okay? Now, the fundamental group of CPR minus the discriminant locus is none other than the braid group. And I will not write the representation of the braid group. I will just say that you have Q1 to QR minus 1 generators, and these are the famous braids, where you basically swap points R and R minus 1, and this kind of, creates this group. Now, there is an action of Qi on this set of permutations. And the action of Qi is actually very simple. You just take sigma I, you move it to the next place, and then you just conjugate sigma I plus 1 by sigma I, and you move it back. And this defines a permutation representation of Qi on these sigma 1s to sigma R. Now, because sigma 1 and sigma R, because these permutations, if you take permutations of R permutation in Sn, okay, and you start acting with Qi, it's clear that you have a finite set. Okay? So, and this finite set is going to define the quote-unquote the moduli space. So now, the action of this pi 1 CPR minus the R and sigma 1 to sigma R defines a permutation representation on this set of sigma 1 to sigma R. So now what you do, you play exactly the same game that I played here, but now you actually play this game on the set of these permutation representations. Okay? You take the sigma 1 to sigma R, you start acting on them with Qi, okay? And you're going to discover, a finite orbit. Okay? By the classical theory, when you look on this orbit, it defines a covering of this space, with a fundamental group being a stabilizer of all permutations. So you take these permutations, you act with these Qis, right? And you find a stabilizer inside this set of permutation representation. So you have, let's say, 20, this Qi gives you 20 permutation, 20 sets like that. You find the stabilizer of one element. And this gives you a covering of this guy automatically. And this is what we call the moduli space, H of sigma 1 to sigma R. And when in the 19th century they thought about moduli space of curves, they thought about this in this fashion. Now, for the usual thing, for the usual space of curves, you just need to take sigma 1 to sigma R to be transpositions. For other, it's becoming more sophisticated. So there is a natural map from this space to the moduli space of curves of genus G. And the question here that I want to ask is, how big is the image? Now, you can go to stable compactifications. You can do all kinds of crazy things to try and answer this question. I'm going to concentrate on G equals 1. So for G equals 1, the image is either everything, that is onto perhaps excluding now finite number of points or finite. Because in G equals 1, the moduli space of elliptic curves is one-dimensional from complex view. Okay, so from the algebraic geometry case, you have no choice. It's either finite or one-dimensional. Okay, so now when it's one-dimensional, you have a very nice criteria to answer this question. So in case of no automorphisms, okay, the fundamental group X and the homology curve X, and I'm going to show this action in reality. So if the curve associated with sigma 1 to sigma r has genus equals 1, then if the fundamental group contains an element of infinite order, when it's acting as a homology base, the moduli mapping is a full dimension. So this answers question in genus 1. So the idea behind this, that if this group acts on the homology basis of this elliptic 1 curve, which is given through this permutation representation, okay, and the image is big. How big? You just need to find one element of infinite order. Then the moduli mapping is onto its full dimension. So generically, elliptic genus 1 curves will carry functions which will give you this kind of permutation representation. This criteria doesn't unfortunately belongs to me, it belongs to Mike Fried. Okay, so now can you work with this criteria? Because the fact that you have this criteria and you doesn't work with it, then it makes it very uninteresting. So here's an example of how you can work with this criteria. So you consider the 4 tuple 1, 2, 1, 3, 1, 3, 2, 1, 3, 2. The product of those guys will be 1. And because we have 4 points, we have 3 braids, Q1, Q2, and Q3, which is acting on it. The action results in 12 signature permutations. So for example, when you take Q2 and you act on 1, 2, 1, 3, 1, 3, 2, 1, 3, 2, using this action that I defined here, okay, you will end up with a permutation of the form 1, 2, 3, 1, 2, 1, 2, 3, 2, 3, 1, 3, 2. In other words, you can think about that you have an elliptic curve which is given with an equation given using and produces these permutations. It will actually transfer it to a curve which kind of given with an equation that produces with this equation. Okay? Now, here's one theorem. The fundamental group of this guy is generated by 3 generators. How do I know that? Here's a proof. It's very easy. It's kind of, by hand. So you find the generators of this fundamental group using the Nielsen-Schreier construction. The Nielsen-Schreier construction gives you basically a way that if you have a free group to find the generators of a subgroup. What you do here, you forget about the fact that it's a braid group. You basically have permutation representation, and you can look on its stabilizer. And you basically use Nielsen-Schreier to find the stabilizer. Now, then you have the braid relations, which I didn't use them here, right? So what you do, you rewrite the braid relation using these generators, and you get the generators in the theorem. So you have a lot of generators. A lot of generators are going to be no longer with us when you apply the braid group relations. The only 3 generators that will survive are those. Okay? Now look on 1 pi 1x. Now, you ask me how you find the homology basis. I find the homology basis because I actually figure out how to do it. And this is a genus 1 curve. The homology basis is given by 2 generators, sigma 1 inverse, sigma 2, and sigma 1 inverse, sigma 3, sigma 1 inverse. What are those generators? Those generators are living inside the sphere minus r points. They are living here. They are living here. They are subgroup of this guy, okay, that you get once you actually fill in those those points back, and you get, and there are two generators surviving. Those are the generators. And now it's easy peasy. Okay, and this follows Nielsen-Schreier commanded with Van Kampen's theorem. So once again, for Sergei, it's going to be basically a child's play to prove something like that, I think. So now we can compute the action of this guy at pi 1 of x. How do I compute? Well, I know how the QIs, right, are acting. I define the action here. Those actions are not just as the sigma 1 to sigma r as permutations, but also as generators of the fundamental group of the sphere. So now I'm just taking these guys, and I'm acting on these elements. And I discover the matrices. And you can see the two matrices are infinitely ordered. So this guy is going to be the full moduli dimension. So two of generators have infinite order. So this guy is finite order. I think these two guys are infinite order. Okay? So it means that G equals 1. So generic curve of G equals 1 is carrying a function of a signature above. So you can actually find an equation for a genus 1 curve. You can find an equation f of xy equals 0, such that when you do this analysis of the analytical continuation, you're going to get this signature. Okay? So it means that it's a 3 to 1. 2 points are coming together, and there are 3 points which are coming together. And there are 3 sheets. Now, other applications. Probably the circle of ideas may lead to fundamental group calculation of complex curves, complex surfaces. Because pi 1 of h is a complex surface when r equals 5. So that's it. I mean, I don't know. Did I actually meet my time, or I have more? Yeah, okay. Any questions?
The question about genus 1 is very interesting because it could be elliptic curve. And as I remember, 3 points have to lie on one line, have to belong to one line in elliptic curve. And the points, if first 2 is have coordinate in base field FP, and third have to be integer 2, have to belong exactly to this field. And this is algebraic group. So is algebraic
yes,
group.
but Ruslan, this is not the traditional representation of the elliptic curve.
Mm-hmm.
The traditional representation of the elliptic curve, which gives you an algebraic group, is going to be y square equals to x minus lambda 1 times x minus lambda 2 times x minus lambda 3 times x minus lambda 4.
Yes.
Okay? But what you see here, right, is not the standard representation. So
sure,
so it's not that trivial to write the algebraic addition law, right, in this form.
Yes, it's something new, absolutely new.
Well, I don't know if it's new or not. I mean, the interesting question to me, whether or not this can be actually extended to moduli spaces of genus G, and I have no idea. I mean, probably this action is extended, so probably you need some measure of that. It's going to be a big enough group or something. Okay.
Yes, understand.
So yeah, so basically you're right. You're right that this raises a question how this is actually related to, if I have something like that, right? How this is related to the usual way that you actually present addition laws on elliptic curves. I agree with you completely. I have no idea of how to answer this question because I have no idea of how to write the equation using this. It's a, you know, it's a kind of an inverse problem. I have no idea of how to do it.
So thank you. It's interesting to see your slides with the friends, and if you
Yeah,
send
I'm
us-
going to send it to you. I have no problem.
Thank you.
There is no secret.
Thank you.